All right, welcome Marina and Jacqueline, Roxine, Marquette, and Sophia, and Jose, and Braulio, and Jacqueline, and Liz. Thanks for coming. And let's jump to the quiz. So here's a quiz. It says the average amount of money that customers spend at a pub is $38, and the standard deviation is $14. You're interested in tables that seat 6 people. Assume a normal distribution. Okay, so then there are a bunch of questions. The first was the last sentence, assume a normal distribution, actually required to conclude that the sampling distribution is normal? Back up your answer numerically. So what do you think? Did we need to assume the distribution was normal? If so,
Yes.
why? If not, why not?
Yes, because it's under 30. The sample size is under 30.
Actually, under 31, right? Because you have to be over 30. So under 31 is so it's if you're going under, then it's 31. If you're going over, it's 30. Does that make sense?
So, but though in that case, do you still have to assume normal distribution with a sample size of 30?
With a sample size of 30, that's not good enough.
Okay, that doesn't answer my question. Do you still have to assume normal distribution with a sample size of 30?
Yeah, that's what I mean. Yeah, so if you have a sample size of 30, you need to assume a normal distribution. Okay, the good news, by the way, is I'd never give you the number 30 on a test because that's like too much of the fine line. But I don't feel bad at all about giving you a 6. Okay, but I just wanted to mention that for the central limit theorem to work for this class, 30 is the boundary. Over 30 is okay. You don't need to assume a normal distribution. And 30 or less is you need to assume a normal distribution. So that's our rules for the class. Does that make sense? Okay, so instead of under 30, you could say 30 or less. That's fine. It's another way of saying it. Okay, so let's type that out. I actually copied and pasted the question so that I can answer the questions right there. So the answer is the normality assumption was necessary since 6 is less than 31. Okay, you could write less than or equal to 30, same thing. Any questions on part A? Okay, let's go to part B. Part B is write down the sampling distribution. So first thing, what symbol are we talking about for this example? So the key, let's read the question. You're interested in tables that seat 6 people. Okay. And if maybe I should have made this as part C instead, but if you're looking at part C, which is find the IQR for the total revenue, because that's what we're going to want, then what are we looking at? How do you write total in symbols?
Sigma.
Yeah, that capital sigma. Okay, which by the way is pretty hard to type. Capital sigma. I think the easiest way to do it is to actually just pop in an equation. And then I can pop in capital sigma. And it's a Greek. I think it's in there. Let's see if it's got Greek capitals. Yep, there it is. Sigma. Okay, if we're writing a sampling distribution, what symbol always goes next after the variable?
Tilde.
Tilde. And then what's the next?
N.
N. Okay. And now, again, if we're looking at the total, because that's what this question is about, find the IQR for the total, then what is the sampling distribution for the total? How do we calculate it? So what's the formula if you want the sampling distribution for the total? Because that's what we're going to need for part C. Do you remember? Okay. Just a note, what I recommend is when you have important formulas that you don't want to have to memorize, have a note card and just write it as we go every week. Write down the little formulas and the symbols that you need to remember in small font on a note card. And that way you've got it. You've got all the important stuff on a note card. And when you take exam 2, you'll be used to your note card. So that's just a suggestion on kind of, working through the class. So anyone remember what the central limit theorem says for totals in terms of the mean?
The mean is the original mean times the sample size.
Yes, it's the original mean times the sample size. The original mean is 38 because it was given, and the sample size is 6. So we can write 38 times 6, comma. And now, what is the standard deviation for totals? Or in other words, what is the standard deviation of the sampling distribution for totals? And that had a formula also. And how did that go?
Root n times the standard deviation.
Yep. So root n times the standard deviation. Okay. I like to write it as a standard deviation times root n. I know it's the same, but the reason I like to write it that way is that way the standard deviation doesn't end up accidentally going under the root. Just looks a little prettier. Okay, so I write the standard deviation as 14 times the square root of 6.
Wait, I thought it was 14. I thought it was the standard deviation divided by the square root of the sample size.
For totals, it's times. For means, it's divided by. Does that make sense?
No.
So that's an important formula. Yeah, for totals, it's times root n, and for means, it's divided by root n. And the reason is when you're doing totals, you multiply by n to get the total. And it turns out sigma over root n times n is sigma times root n. A little bit of algebra. Any questions on part B? Okay, part C is find the IQR for the total revenue for tables that are filled with 6 people. So who remembers what IQR means?
75th percentile minus the 25th.
Yeah. So I'm going to write down, I'll write it in the symbols that we're used to, which is Q3 minus Q1, which is the 75th percentile minus the 25th percentile. Any questions on that? Okay, so now what we can do, so you can go to the calculator, which I decided to just directly embed it, so you don't have to go anywhere. It's all there for you. And which calculator do we need?
Normal probability.
Yeah, we need the normal probability. That was the tilde n. Tilde n means normal probability. We want the 75th percentile. So the low is, so 75th percentile means that number, and below has a probability of 0.75. So and below means you go as far as you can. Negative 99999 is a bunch of nines. Okay, the high is what we want. So that one we leave blank. The mean, and if you remember, the mean was, let's put it in there. The mean is 38 times 6. So what I'll need is my scientific calculator, if you don't have it. So 38 times 6. And it gives you 228. So the mean is 228. The standard deviation was 14 times the square root of 6. So I'm going to go to my calculator. And I can go 14 times, and then the square root button, and then 6. And it's 34 point messy stuff. So let's pop that in. And what's P? So what's P?
Which quartile are you trying to find right now?
We're doing Q3 minus Q1, so we need Q3.
0.75.
Yeah, 0.75. And hit calculate. And there we go. My high, or my Q3, is 251.13. I'm just going to call it 251. It's good enough. So equals 251 minus, and now we want Q1. And the good news is we've done most of the work already. We want Q1. So instead of 0.75, what do we have? Instead of 0.75, what do we get? Yeah, 0.25. And then again, the high is what we want. So I leave that one blank and hit calculate, and you get 205 is good enough. Okay. And you can use a calculator. I can do it in my head. That's just 46. And there's your IQR. Any questions at all? Any questions at all on this first quiz question? Okay, I will let you know it's a pretty standard question. The main thing you need to do is practice, and there's 3 types for the central limit theorem. There are, sorry. Yep, I tend to do that a lot. I transpose numbers. That, by the way, and this was really important in the test. If you're like me and you make mistakes sometimes, and everyone makes mistakes, but just in case you don't think you're perfect, then by showing Q3 minus Q1 equals 251 minus 205, and if I wrote equals 64 and it was a test, you're going to get most of the credit. Okay, I might take like a half a point off or something like that, but that would be it. So the point is showing your reasoning is crucial. Okay, and if it was an exam, I'd write down what I use for the low and the high and the mean and the standard deviation and the P. Okay, so just a note, always a good idea. Any questions at all on this question about totals? Okay, if not, let's move on to the number 2. Okay, according to Gallup, okay, 55% of Americans think that the income tax that they pay is fair. Okay, all right, but this is a recent article, by the way, last week. If you randomly selected 100 Americans, asking them if the income tax they pay is fair, A is your sample size large enough to conclude the sampling distribution is normal? Back up your answer numerically. So what do you think? Is it a big enough sample size, and why is it a big enough sample size?
Yes, because it's over 31.
Okay, be careful. What's the survey question here? What's the survey question? Right? What are all these Gallup poll people asking people? So what is the survey question? And it's very important for this class to always focus on what is the survey question, and then based on that, we'll be ready to answer. What's the survey question? What are the Gallup poll people going to ask? It's not written here, but it shows basically. I don't see y'all jumping in. So read the first sentence. That's the hint. So what would the survey question be? Still don't see jumping in. Okay, they're saying 55% of Americans think the income tax they pay is fair. So if you're going to ask a bunch of people to find out the percentage of Americans that think the tax is fair, you're going to ask them, do you think the tax you pay is fair? Okay, let me ask you, what do you think? If I asked you, do you think the income tax you pay is fair? Tell me what you say. You can put in the chat box. Okay, so notice no one is saying numbers. Okay, this is a yes or no question. It's not a quantitative question. When we have yes, no questions, what is the key information you need to show that the sample size is big enough? Do you remember the number? It's not 30 and 31. And remember that number. It's very important. I don't see y'all jumping in, but it's going to be important on exam 2. If you don't know it, it's going to bite you. Okay. So the key number on the yes, no question is 5. And it's not sample size being bigger than 5. It's NP and NQ being bigger than 5. Do you remember that? Hadn't been that long, just a week. Okay. So we need to check NP and NQ to see if they're bigger than 5. N is 100. P is 0.55. Okay. You don't need a calculator to do that. Hopefully you don't need a calculator to do that. So what is 100 times 0.55? Nice and easy. Try to give you really easy numbers here. What do you get? Yeah, 55. And that is bigger than 5. And let me write down the symbols just to show you. That's NP. And we also need NQ. And NQ is 100 times 1 minus 0.55 or 0.45. And that's 45. And that's greater than 5. So therefore, the sample size is large enough to conclude that the sampling distribution is normal. Any questions on that? Any questions? Okay, part B is write down the sampling distribution. So first, what is the variable or the symbols that we're going to use for this? And you can write them out because there's no way you're going to be able to get the symbols nicely in the chat box. It's even very hard on Canvas, but writing that's fine. What's a symbol when they have the yes, no question? Yes, p hat. So p hat and then tilde and then n. Okay, and what is the mean of the sampling distribution? The hint is it's very easy. What's the mean of the sampling distribution? Yeah, 0.55. Because the mean of the sampling distribution is just your proportion, your p, which is 0.55. On the other hand, the standard deviation is messier. That was the square root of PQ over N, which is 0.55 times 0.45 divided by N, which was 100. Any questions on the sampling distribution? Okay, now we go to part C. Find the probability that at most 50 of your sample will say that the income tax that they pay is fair. Okay. So by the way, if 50 people say that it's fair, what percent said it was fair? It's very easy. That's a hint. Super easy. If 50 people said it was fair, and you asked 100 people, what percent said it was fair?
100%.
50 people said it was fair, and from the 100 that you asked, that wouldn't be everyone. That's only 50 of them.
Wait, no, you said, but wait, but you said you asked 50 people.
No, I said
And
of the
50
100
people said
people you
yes.
asked.
You said
Oh.
you asked 50 people.
I think you may misheard. So it's if 50 people said that it's fair of the 100 people that you asked. We only asked 100. That's what this question says. Then what percent said it was fair? Yeah, 0.5 or 50% or 0.5. The other thing is, what does the word at most mean? So what do those two words mean? At most. I don't see y'all jumping in. So at most, does that mean big numbers or small numbers if it's at most 50? $50 would be the highest or lowest. Yeah, that's what I said. So what does at most mean? What inequality is it? Is it a less than or a greater than? Okay, and less than or equal to, but the equal doesn't matter with normal distributions. So what does at most mean? Yeah, so that's a low number. So that means less than. Okay, that's really important to get that. So we want to find out that less than 50%. What is that probability? So let me write that down. That means probability that p hat is less than 0.5. Now we're ready to go to our calculator. And we have 0.55 was our key number there. So let's go to our calculator, normal probability again. Our low will be negative. Actually, the low technically is just 0 because you can't have under 0. But negative 999 is probably better if we're assuming normal. It turns out it doesn't make any difference. The high we leave blank because that's what we want. Oh, sorry, the high we don't leave blank. We leave it as 0.5. Apologize for that. The mean was 0.55. The standard deviation was messy, so I need to go to my calculator. And I need to get the square root. And then I'm going to go 0.55 times 0.45 divided by 100. And that's this guy, 0.0497, bunch of other numbers. So I'm going to copy and paste it, pop it in that standard deviation. And we want P, so we hit calculate. And it looks like about 16% chance. I'll just grab a bunch of decimals and then I can paste it in. Any questions? Any questions at all on this quiz? Any questions? Okay. I do want to give you a heads up, and that is exam 2 is not for a long time because you just took exam 1. It's, it's like in 3 weeks or something like that. So promise me that in a few weeks, before you take exam 2, that you'll practice problems like this. You can always go back to the webinar. You can watch it and you could redo the quiz just by that, and you get to see the answers. So it's very important that you practice so that you refresh your brains, because it's very easy to forget. Even if you learned it this week, 3 weeks from now, you may have forgotten by then, and that's why you want to practice. So hopefully you'll practice. My guess is those who did well in exam 1 probably did practice the earlier stuff and later stuff and got it and understood it, and and those that didn't may not have. Okay, they may not have understood it, and they may not have practiced it, one or the other. Any questions at all on the quiz? So I'm going to submit my quiz. Okay, let's move on to the next piece of what we're doing today. So we just did the quiz. Now it's time for questions. Are there questions about anything?
Oh, are there any suggestions from question 19 that you're going to be taking that we should be aware of going forward?
There's going to be small stuff. I might add a couple links to the modules, because there are a couple requests for that. And there's not going to, I'm definitely not going to say, well, we're going to erase the whole syllabus and start over again. That I wouldn't do that anyway. But there'll be smaller detail stuff. Just note, some people wanted more example videos. And I hope you realize there are a lot of example videos. Okay, there's example videos for every chapter that are short videos, and there's also a long chapter video that has many examples. So just note that there are lots of examples in these videos. So there were a group of you that wanted more examples in the videos. So that's where you're going to find more examples. Does that make sense? And in fact, if you go to the syllabus, you'll see that there's full-length YouTube lectures, and there's also short introductory videos of each week. Well, that one's not examples, sorry. Videos of worked out problems. So there's a video of worked out problems. So there's a lot of example videos for you. So that's something that is already up there. Some of you wanted things in the modules, so I might add some stuff to the modules. There were more general. There's some of the general comments which there's not a whole lot I can do about, but those are the main things that I can do things about, is adding things to the modules and reminding you that there's all these videos. Does that make sense? Those are the main things that I saw in the extra credit, problem 19, okay, which was an extra credit question. Hopefully that answers your question. Some people wanted things that there is not enough details to talk about, kind of stuff. Any other questions? Any other questions? Okay, I thought I'd just mention the exam, talk about it a little bit. And I believe, yeah, you're not gonna be able to see it until I reshare. Just a minute. Takes a moment. I'll have to get there. So let me do new share. Because the exam key I actually made in Microsoft Word. So that means I have to reshare. So hopefully you can see it. Okay, so I'm not gonna go through every little detail of the exam because that'll take the whole time, or a lot of the time. But I want to talk about some of it, and especially where people had troubles. So the first thing is this is Thursday's version because it was the same exam for the Thursday class as it was for the online students that took a Thursday, but they also had Saturday and Sunday, just to note. So for the first one, the idea here, I think a mistake that I saw there multiple people make was forgetting the boundary for outliers. Okay, did you guys see my comments that I put in? That I put directly into your exam? Hopefully you got a message about that. Okay, so you should be able to see the comments, but I want to kind of emphasize the things that more than one or two people made the mistake on. And that is outliers occur when the Z value, the Z score, is less than -2 or greater than 2. There were people with 3 and 1, and those were not the right numbers. Z needs to be less than -2 or greater than 2. And the idea here is you don't just make up some numbers. You need to look at the data, and you got to look for outliers. And the way you look for outliers is you just find what is the minimum, and you'll notice the minimum is 3. So you find the Z score and use the mean of standard deviation by the calculator. You find the Z score when your value is 3. And when you do that, I got 2.32, -2.32. So that's an outlier. Then you go to the next number, and that's a 4. 4 is too big. It's negative, it should be negative 1.89, so that's not an outlier. And then you don't need to look at any other small numbers, because once you don't have an outlier, anything closer to the mean will not be an outlier. So then you look at the big numbers. So the biggest number here is 16. And if you plug in 16 into the Z-score formula, you get 3.3. That's an outlier. It's bigger than 2. Then 14 is the next biggest number. And plug it in, you get 2.44. So that's an outlier. It's bigger than 2. And then the next number below 14 is 9. And the Z-score for 9 is 0.77. So that's not an outlier. So that means that 3, 14, and 16 are the outliers. Stop me if you have any questions on any of these. Any questions? Okay, so if no question, I'm gonna move on to the next one. So the next one was the biggest mistake people made about this next one was not to use the binomial distribution. This is a classic binomial question because we have 23 trials, and the survey question is do parties do a poor job representing American people? Okay, so that a third party is needed, and the person's going to say yes or no. And with a yes/no question, and you're asking many people, then that's binomial. Okay, most people, just about everyone who knew that it was binomial got it right, but there was a group of you that didn't know to use binomial. It wasn't supposed to be a trick question. That's classic binomial. It's a bunch of trials with yes/no questions. Any questions on the second? And when I say the second question, I mean the second kind of question where there's work to do. The true falses and stuff are different. Okay, there wasn't work to do. That was just vocabulary, basically. Okay, the third one was the expected value problem. Okay, and one thing that some people didn't do or they forgot is that if you're paying $5 and you get a check for $1,200, then your profit is $1,195. You got to subtract the 5 from the 1,200. And similarly, you got to subtract the 5 from the others. Okay, so the X's were where some people had troubles. P of X is not a problem. What I found is most all of you who got the who had a distribution table were able to get the expected value and standard deviation using the calculator. So that wasn't a problem. And maybe you can give me a suggestion because I have not figured out how to get you guys to use the keywords in expected value problems, and that is likely, average, many, and close to. Okay, so those are 3 key terms, 4 key terms that must be there. And I warned you, but warning isn't enough, I guess. I'm not sure what I can do. Any suggestions? How to like convince everyone that you need to do that or you're going to lose points? Other than saying it 7 times? But if you have suggestions, let me know. Tell them I get a 0. Yeah, but I'm not that evil. And I don't lie either. So I won't tell you get a 0 and then not give you 0. So that one I won't do. I'm not a liar. Sorry. If you want me to be a liar, it's not going to happen. So I won't tell you can get 0, but I will tell you lose points. And I did take a point or 2 off, which is, because it was a 3-part problem. So C was worth 5 points and you lost a point or 2 for not having the keywords. Okay. And a lot of you didn't. And you get a note card. Put them in your note card. So I'm not sure what to do, but it was important. And there's going to be keywords today too, by the way. For the chapter this week, there'll be some keywords. Okay. For the next one, the distribution. Hopefully, what I was looking for is unimodal, symmetric, normal. Okay, those are kind of the statistics words we've used to describe a distribution like this. Approximately normal is probably better than exactly normal, but this is about as good normal as it gets for real world situations. Any questions on that? Okay. So part B is if we have an additional company that has a quarterly return of negative 0.5, which is down over here. What will happen to the standard deviation? What happens to the standard deviation when you put in an outlier? Always. If you add an outlier, what always happens to the standard deviation? I don't see you jumping in, but so we got an outlier. The standard deviation is the average distance from the mean, or an average distance from the mean. So if I have a bunch of numbers, a lot of them real small, and all of a sudden I add a really far away number from the mean, and I take the new average, what's going to happen is they're going to go up, down, or stay the same. So if you add something very far away from the mean, and we're talking about the average distance from the mean, will that average go up, down, or stay the same? I don't see y'all jumping in. Some of you got it right, so you should know. I don't think I'm on mute. I think you can hear me, but maybe not.
No.
You can't hear me?
Oh, no idea.
No idea?
No idea.
Okay. So if you have a whole lot of, so you got a whole lot of people that are all close to 0 from the mean, and then you throw one, not a person, but a return, and then you throw a return that has a very big distance from the mean, and now you take the average. Well, if you used to have just a lot of little numbers, and now you have a lot of little numbers and a big number, okay, distance from the mean, and now take the new average, then the average distance will go up. Okay, if you insert someone that's got if you have a bunch of numbers that are really tiny, and you take an average, you'll get a really tiny number. Okay, but now if you take those numbers that are tiny, and then add a giant number and take the average, it'll be bigger than you had before. And that's what we're talking about. And it's a distance, so it doesn't matter whether it's left or right. The average distance will go up. Okay, very important. Outliers always increase the standard deviation. Okay, on the other hand, part C is if you had 1,000 companies that are returned 0.02, which is the mean. Now we're taking all these numbers. They're pretty low, but not all 0. And we're adding 1,000 zeros from the mean. 1,000 that are 0 distance from the mean, now taking the average. So now what'll happen to the average? Right?
Average distance will decrease and the standard deviation will go down.
Yeah, the average distance will go down because if you throw in a whole bunch of zeros and now take the new average, you're going to have a smaller average. Does that make sense? Okay, a lot of pop-up people had trouble with that. I'm not quite sure, how to make it work. Okay, so the next question was a probability question. And it says Latinos make up 36% of the California college students. Okay, but they represent 39% of California community college students. 69% of all California college students are at community colleges. Okay, so what I like to do before I even answer all these questions, I'm just going to put all these numbers as probabilities. Okay, so I'm going to say probability of L for Latino is 0.36. Okay, on the other hand, 39%, they represent 39% of the community college. So of the community college, it means we're given they're a community college student, then we're looking at the probability of Latino given community college, and that's the 0.39. And then we know 69% are community college students, so probability of C, community college student, is 0.69. We want the probability that a student, this is a hard question for some people, okay? I'm trying to go over it, so ask questions if you don't understand something that I'm saying. Okay, if you want the probability that a randomly selected student will be a Latino at a community college, well, that means they got to be both. They got to be Latino and they got to be community college for them to count. So that's an and. Probability of L and C. And then we had a little formula. That's the probability of C times the probability of L given C. And they just multiply the numbers. 0.69 times 0.39. And you get 0.2691. Any questions on that? Okay, part B. Find the probability that a randomly selected California Latino student will be at a community college. So now we know they're Latino. We want to see the probability of their community college. So that's probability of C given L. And we had a formula for that. That's the probability of C and L divided by the probability of L. C and L, that was part A, 0.2691, divided by the probability of L, which is 0.36, and you pop it in the calculator. Any questions on B? Okay, C was Latino or community college. So that's probability of L or C. And the formula is probability of L plus probability of C minus the probability of L and C. So I just plug in because I know all these numbers. They're given above, and I get my answer. Okay, then are being Latino and being community college student mutually exclusive, independent, both, or neither? Back up numerically. So for mutually exclusive, definition of mutually exclusive means that the probability of both of them happening is 0. But the probability of L and C is not 0, it's 0.2691. That was part A. So it's not 0, so they're not mutually exclusive. Okay. For independent, you get to look, you get to choose, and we're given, either C given L because we just did that one. And that was 0.7475, but the probability of C is 0.69, and those would have to be equal for them to be independent, so they're not independent, therefore they're neither. Who's lost on what I just did? Any questions? Any parts, A, B, C? There was a typo here, I apologize, and that should have been D, but I made it E, but hopefully that wasn't the problem. Any questions? Okay, let's move to the next one. Okay, suppose air pressure of tires considered safe is uniformly distributed between 31 and 40 PSIs. Show your work. Okay, so the first thing that I'm going to need, so I'm just going to do it before I even answer any questions. I'm going to find the height. We know that uniform, and a mistake a lot of people made, and I'm not sure if it's just not reading the question, is a lot of people did normal distribution on this, and it's uniform, it's not normal. Okay, and I'll let you know, I'll remind you that last week, so a week ago today, I went over what the exam was going to be, and I told you that this problem was going to be about uniform, and the next one was about normal. So some of you got confused, but it says uniformly, it's not a trick question. So that means we need the height, area is base times height. The base is going to be 40 minus 31, because that's given. The height is h. Okay. And that has to be 1, because it's the whole thing is between 31 and 40. So I get h equals 1/9. Any questions on just getting h? Okay. That was a big piece of it. Now let's do part A. Find the probability of randomly selected safe tires. Air pressure is between 34 and 36. So again, area equals base times height. So I take the base, which is 36 minus 34. The height was 1/9, and I get 2/9. Any questions on part A? Okay, for part B is what's the third quartile? So now, third quartile means the probability is 0.75. So area is base times height. We don't know the right end, so call that x. X minus the left, which is 31, times 1/9 needs to be 0.75. So I multiply left and right by 9, and I get x minus 31 equals 0.75 times 9. Add 31 to both sides, and I get 37.75. Any questions on part B? Okay, mean and standard deviation is just plugging into the formulas. I'll let you look through that. But formulas, you can have your note card, you just plug in. Okay, and you were given a calculator, by the way, okay, in this problem. And then find the z-score, and you just plug in. So that's 39 is our x minus the mean divided by the standard deviation. Any questions at all on this question? Okay, let's get to the next one. Okay, suppose the time it takes competitors to run a 10K is normal, and the mean is 58, standard deviation is 10. So we want the probability you're going to finish in less than 53. So simple calculator work. Most of you got this right. So less than 53 has a low of negative, a bunch of 9s, high of 53, mean, standard deviation, you just plug in the calculator. What is the 27th percentile? Here, that means that we know the low is negative 99999. The mean, we know. The high, we don't know. That's the question. The percentile is the high. And then we make sure that our P is 0.27. And when we do that, you get 5187 in the calculator. Okay, So A and B actually for a lot of you are easy, but C was hard. A lot of you had trouble with part C. And my definition is hard means that most people didn't get it, whereas easy means that most of you got it. So A and B were easy, C was hard. So if you were observing a runner who is still running after 59 minutes, so that means we know that the person ran at least, it took at least 59 minutes to finish. So that's a given. What's the probability the runner will take longer than 62? So that's a probability that X is greater than 62, given X is greater than 59. So I want to stop because very few of you got that. Any questions on reading the sentence and writing down this given probability? Any questions? Okay, once we have that given probability, then we can use the formula that says the probability of A given B is the probability of A and B. But if you're both greater than 62 and you're greater than 59, then you're greater than 62. Okay, there's no new information to be told of greater than 59. So the probability of greater than 62 divided by the probability that X is greater than 59. So that means there's going to be two different normal distribution questions in here and then divide. Okay, so the first one's the low is 62, the high is a bunch of nines, mean is 58, standard deviation is 10, and I get 0.3446. Similarly, the second one, same exact, except the high is 59. Sorry, low is 59. And then the probability is 0.4602. Then divide, and you get about 7.7488. Any questions at all on part C? Any questions? Okay, so now let's go to the last question of questions that you actually had to do math. And that is a box and whisker plot shows the age distribution. So here we go to box and whiskers plot. Part A and part B were basically, do you know how to read the plot? So what age is at the 65th percentile? So let me ask you, what percentile is the number 26? What percentile is that?
50th,
That's the 50th percentile. What percentile is the number 42?
75th,
75th. We want the 65th percentile, which means it's going to be a number between 26 and 42. Has to be bigger than 26 and less than 42. Okay. For example, 37, I would have accepted any number you gave me that was bigger than 26 and less than 42. Anything, if it was smaller than 26, you're less than 50th percentile. If it's greater than 42, you're greater than 75th. So 37 works. If you did 41, I would have accepted it. 29, I would have accepted. Okay, any number in between them. Any questions on that? There's nothing to do with the normal distribution, by the way. Nowhere does it say normal. So there's nothing to do other than look at the picture. Okay, now B, what's the probability the randomly selected student will be between 17 and 93? What percentile is 17? Yep, 25th. And 93 is a maximum. That's what box plots, that's how you read a box plot. So what percent is above the 25th percentile? Yeah, 75%. And that's part B. Any questions on A and B? Okay, there's no work to show. You just look at it and answer the question. It's very quick if you know how to read the box plot and are thinking that, yeah, I'm just reading the box plot. Okay, part C, there's a little bit of work. Okay, because now we have 16 students randomly selected, not one student. What's the probability exactly 4 of them will be between 42 and 93 years old? Okay, so 42 to 93. What's the probability that one of them will be between 42 and 93? Just one person, not one of them. Sorry. What's the probability if you pick one person that person will be between 42 and 93? One student. Yeah, that'd be 0.25, 25%. Okay. But we're picking 16 students. Each have the same probability of success, being between 42 and 93. So this is binomial. So the low is 4, because it's exactly 4. The high is also 4. Number of trials is 16. Probability is 0.25. You pop in the calculator and you get about 2252, if I remember right. Okay, and that's it. And again, the last question was the extra credit, which, by the way, is the last extra credit and the only extra credit for this whole course. Okay, so there won't be an extra credit on the next exam, just the first exam. Okay, because now hopefully you know what you need to do well in the exams. Okay, you know what my exams look like, at least you get the idea. Any questions at all on the exam? Any questions? Okay, if there's no questions, I'm going to go back to our to-do list. We're done talking about the exam. And I want to get into what's called confidence intervals for a mean. So what I want to do first is I'm going to ask you a question. And just to let you know, this is very important. When I ask you a question that's personal in this class, you don't have to tell the truth, but you just have to give me a number because I need data. That's all I want is data. But my guess is you'll be okay telling the truth. So here's the question. And I've been asking this. This is my 25th year of asking, because I've actually noticed a very interesting trend, which I'll talk about later. Question is, how old were you when you experienced your first passionate kiss? Everyone's required to give me a number. It'd be nice if you gave me the truth. Don't give me, if you want to lie, don't give me 950 years old, because that's stupid. Give me something that's at least reasonable. And by the way, no one can see this on YouTube because it goes in the chat box. Chat box doesn't get put into the YouTube. So this is just us. But even if you don't feel comfortable amongst us, you can just put in a number. And this is for everybody involved in statistics classes. So I actually put my number in too. Maybe I'll put it in now. That's how old I was. So how old were you when you got your first passionate kiss? So everybody needs to put in the chat box. Everyone in the class. But again, you don't have to tell the truth, but it'd be nice if you did. I'm not going to use it up for you, against anybody or anything like that. Okay, so what I'm going to do, because I'm going to do, these are people involved in the stats class, I am going to include my other stats class, because I asked them last night. Okay, and that includes me, by the way. So the other class, by the way, 14, 19, 14, 13, 22, and 16. I'm the 13, by the way. Okay. And we got 15, 17, 17. Seventeen, 13, 17, 17. And I think that's it. Okay, so that's my sample. Better than last night because we have a bigger sample size. Last night was really small, but now it's a little bigger. Okay. By the way, I got a fun question, not a stats question for you. Do you think, I'm the youngest of this group, do you think I was young or old compared to like all the people in my classes when I was 13 years old to have the first passionate kiss? Do you think everyone looked at me and said, wow, you're so lucky you got to kiss that person? Or do you think they're like, God, you're just old? What do you think? Any thoughts? This is not a stats question. Okay. It turns out I was like the oldest of anyone I knew to have my first kiss, and I was 13 years old. And I have been asking this for 25 years now. And I have seen a very interesting statistical pattern. So I'm talking about this because of stats. And that is when I started teaching this, the numbers were all 13, 14, 15, basically. Now, lots of older people, lots of people waiting and waiting and waiting. And that's actually a big change in our society. So if anyone's a sociology major, for example, you might learn about this kind of stuff, is that modern society, people are waiting to have kisses. And then, of course, you know, hopefully much after the kiss, then people get a lot more involved and they have sex. Everything has changed. And then they have a child. And when I was a kid, people were having kids in their teens. Now it almost never happens. Okay, it's very rare. So I'll let you know. And I have watched the statistics in the last 25 years and I've noticed it. Okay, but here we have it. This is our group of people. Any questions so far? So what I could do, always a good idea. I'm going to copy this and go to my calculator. And I'm going to go to one variable stats. Pop in my data. This is a sample. We'll call it Californians involved in statistics classes. Okay, maybe I shouldn't say California because not everyone's from California. How about US people? I think everyone's in the United States right now. Okay, hit calculate. And I get a mean of 16, about 16.2. Let's write that down. What symbol is the mean, by the way, in this case? What's the symbol I use for the mean? Yeah, this is the X bar. Takes a moment to make the bar happen. There we go. So X bar is equal to 16.2. All right, and then I get my standard deviation was about 2.5. What symbol is the standard deviation? Hint is that's easy to type. You could write SD, but for this one, actually, you don't need to write SD. What's the symbol we use? It's a single letter. Simple. It's S. So very important you get down the symbols. So the sample mean is X bar. The sample standard deviation is S. All right. So I'm looking at my clock. It's 4:59. I think it's a good time for a little break. I like to give you a break. I'm supposed to actually. I like to give you a little break, 5-minute break or so in between. So why don't we come back at probably 5 after by the time I finish saying come back. So I'm going to stop and then we'll come back at 5 after. Okay, let's get back. Hopefully you had a nice break. So let's go and get back to what we were doing. And that was seeing what the age of first passionate kiss is for kind of all people, not just us, but all people involved in statistics classes. So let's go ahead and I'm going to reshare my screen. Okay, so here's a question for you. Do we know that the population mean for all people that are involved in statistics, let's say United States, is 16.2?
No.
No, we definitely don't know that. We have a sample. We didn't ask everyone in the United States. So here's a more difficult question. Now that we know our sample mean 16.2, that's our best guess. It doesn't mean it is 16.2. But do you think it is likely or unlikely for the average age to be less than 12, given that we got 16.2 from this sample? We're going to assume it was a random enough sample. What do you think?
No, it's not likely.
No, it's not likely because note the standard deviation is 2.5, right? And that's pretty far below. So a 12 is pretty far below 16.2. Does that make sense? So it's not that likely. And the standard deviation is 2.5. That's the standard deviation of the sample, but not of the sampling distribution. Our best guess for the standard deviation of the sampling distribution will be 2.5 over the square root of n, which is what? 2, 4, 6, 8, 10, 12, 13. So 2.5 over root 13, that's like 2.5 over 3 or 4 or so. So it's less than 1. So even 13 would be way too young because that's already like 3 or 4 standard deviations lower. Does that make sense? What if I asked you about, say, 16.1? Do you think it would be like unreasonably unlikely for the population mean age of first kiss to be 16.1? Based on what we've got here? What do you think? So do you think 16.1 is a reasonable number? Do you think that's so far away from 16.2 that it wouldn't be reasonable? What do y'all think?
It would be reasonable.
Yeah, that'd be reasonable. The standard deviation, again, a little under 1, but not much under 1. And 16.1 is only 0.1 under the mean, the sample mean. All right, so let me give you a picture. So here's a picture, okay? And it's kind of the picture for this class. And that is the normal distribution. Now we're going to assume that we have an approximately normal distribution for the sampling distribution. Okay, we need to assume that. We need to assume that the population distribution is normal because our sample size here was too small. I will let you know that you should never conduct a study with such a small sample size and think you have good data. So I'm only doing this because it's all I've got. But I would never use this to publish anything, but I'm just giving it as an example for our class. But in the real world, you should get at least over 30. So you truly get a normal distribution. So here's our X bar, which was our about 16.2. And what we want to do is we want to say, well, how far to the left and how far to the right are we willing to go and say that it's still reasonable? We decided that 12 was not reasonable, but 16.1 was reasonable. So the big question is, what is this barrier on the left? And what is this barrier on the right to talk about what's reasonable? Any questions on that idea? Okay, so it turns out that the standard way of doing things is you make sure that the area under this curve, or the probability of being between those two numbers, the standard is 95% or 0.95. So we call that the confidence level, or CL. So CL stands for confidence level. And 95% is standard. It doesn't mean everyone uses it, but I will tell you political science, sociology, psychology, all the social sciences, they all use 95%. Do you think there'd be a case where you'd want to 95% wouldn't be enough? Because if you have a 95% chance that you're actually going to have that mean in your little interval, there's a 5% chance that you won't have the mean. Can you think of an example or an area of the real world where you might want to be more than 95% confident about something? Okay, skydiving is a good one. I like skydiving. I wasn't thinking about that, but that's a good one. Okay. So if you're looking at the, proportion of people that get hurt or something, yeah, you might want to not be off by much on that one. Okay. That's a really good example. Let me give you a kind of a main example for a lot of people in this class, at least, and that is
Scuba
healthcare.
diving.
What's that?
Scuba diving.
Yeah, scuba diving, but that's not a lot of people in the class. Healthcare. There's a lot of people that want to be nurses or go into medical. So I want to mention that because that's a big place where stats students kind of congregate, is through the health science majors. And so, for example, the vaccine. Okay, I'm not sure if y'all got the vaccine yet. Some of you might have, some of you haven't. But what they did is they did a study, and they had participants in the study. And do you think having a 5% chance that the vaccine just doesn't really work, do you think that's good enough? Would you be okay with that? Probably not. Or if there were some awful side effects and you were off by 5% of your probability.
There are awful side effects.
What's that?
There are awful side effects.
I don't mean the one day after you feel horrible. I mean people dying.
Oh, that's true. But
yeah, I don't mean just feeling miserable the day after and then 2 days later you're great. I'm talking about really bad ones, like death. Okay, or it just doesn't work. That would be bad.
What happened
too.
with Johnson & Johnson?
Yeah, Johnson & Johnson had it, but actually a very, very small percent.
Yeah,
so
fair
they
enough.
raised a red flag and they got a bigger sample size. That's what they did actually. So it was a very small percent that actually had troubles with Johnson & Johnson, but it wasn't zero. And that made people scared. Just let you know, if you look at the numbers, look at the data, and you look at the percentage of people, it's a very, 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 very small percent. But it was enough for there to be concern. Okay, so let you know, for things like that, usually go for 99% is kind of a standard if you want to be very confident. There are other times I let you know that I do consulting work, and I consulted for the Forest Service, and they told me they wanted 90%. And you know what you say, the boss is always right. So I said, sure, I'll do a 90% confidence interval for y'all, looking at your data. And I did that for them. Okay, again, it's their job to decide what is good enough. Okay, so they wanted a 90% when I did some consulting work for them. And I can't tell you that that's true of every Forest Service study, but for the study I helped them with, they wanted 90%. So I'll let you know that you'll see 90%, you'll see 95%, you'll see 99%. 95 is the standard. Just let you know that. Okay, all social science uses 95. I've never seen anything other than that in social science. And political science, news, always 95. Okay, but medicine's different. Okay, so E. E stands for error. because the idea here is our best guess was 16.2. And the error is how far you're willing to go left and right with that 95% confidence. So the 95% is this area, and the error is how far left and how far right. It's the same distance, it's symmetric, that you're willing to go. And that all depends on the situation. Okay, so if you cared about age of first kiss, I don't know, you might go a half a year, because no one really cares whether the age of first kiss is 16.23 or 16.24. Okay, that's for the average age. You care about you personally, which day you got your first kiss. But if you want to look at the average age of first kiss of people in statistics, then you don't care about 2 decimal places. I can't imagine that. You might care about maybe a half a year, because that means that you're rounding right. Does that make sense? So E might be, a good E might be 0.5. If you want to take your 95% confidence and go to 99, that means you're decreasing the area, because it's always better to be more confident. But if you decrease it, you're increasing the area if you go to 99. But if you increase your area, that means you're pushing the left boundary to the farther left and the right boundary farther right, and you're going to have a bigger error. So it's a trade-off. If you go to a higher level of confidence, then you're going to have a wider spread. Whereas if you're going to have a lower level of confidence, you get to make your spread lower. Okay, so let me give you a kind of an easy to think of example. Okay, what if I told you with 99% confidence that the average height of college students was between 3 inches and 12 feet tall? What have you learned from me? Nothing, because you already knew that. 3 inches to 12 feet. Of course, the average height is somewhere between there. But yeah, you're very, very, very confident. So if you get more confident, you're going to get an average. You're going to get an error that's so wide that it's useless. On the other hand, what if I told you I was 20% confident that the average height of college students was between 5 foot 5.1 and 5 foot 5.2? Are you satisfied?
No.
No, because it's a 20% confident. That means that there's an 80% chance I'm wrong. Do you see that? They're both bad. Does that make sense? So if you want to have a higher level of confidence, you got to give up a small error. And if you want to have a small error, you got to give up the high level of confidence. Unless you do what? What's the one thing you can do to make so that you can have a high level of confidence and a small error? Any thoughts? And it comes from the central limit theorem. The only thing you can do. Yeah, increase the sample size. Because if you increase the sample size, the standard error goes down. So if, for example, for the vaccination, they increased the sample size because they wanted that high level of confidence and they wanted a small error. So anyone know the sample size for the vaccinations? Do anyone remember? For Moderna or Pfizer, they were pretty similar. Not exactly the same, but they were similar. And you remember the sample size? 15? No, definitely not. Oh, 15,000. Okay, that sounds a little better than 15. It was more like 35,000. So it's 35,000, very big sample size, which means they were able to have a high level of confidence and a small margin of error. Any questions on that? Okay, so I wanted to show you the picture and give you an idea of what's going on. Okay, what I'm not going to do is I'm not going to make you compute this by hand. Okay, Instead, how do you think you're going to compute our left and right bounds? So we have this, our data. How do you think we're going to compute the left and right bounds? Any guess? Oh, what's CL in the picture? Confidence level. So the standard CL is 0.95. Does that make sense? So that's CL. CL stands for confidence level. Okay, so how do you think we're going to do this? The easy way. The hint, it was hard for me and easy for you. Any thoughts? Yeah, we're going to go to the calculator. It was hard for me because I had to program the thing. Okay, and trust me, it took a lot of work. Okay, so I'm going to go back to my calculator menu. See if you can guess which one we're going to do. It's our first time doing it. And pretend we just got our numbers. We could do statistics, but if we just got our data and that's all we had, we're going to do number 10. So we have the data. So let's do number 10. Because again, I rounded to one decimal place, which probably isn't very good. So I'm going to do a confidence interval for a mean with data. Okay. So I'm going to go and copy and paste the data. And what do you think CL should be for this? What would you like your confidence level to be for this kind of problem, for this kind of question?
Probably 90 is fine.
You could do 90. You probably wouldn't do 99 because no one's going to die on this one. But this is a sociology question. Age of first kiss is like true sociology or psychology, whichever way you want to look at it. Do you agree?
I mean, I think that the question itself would be more interesting where it's like actually trying to analyze something about, like, let's say gender differences or sexual orientation differences and having your first kiss to like gather data from that point of view. But in terms of this, I don't.
Yeah, this is definitely sociology or psychology. You know.
Oh, I'm aware of that. I'm just saying, like,
So sociology and psychology use
fine.
95%. That's what I'm trying to tell you. They use 95%. So I'm going to use 0.95 because this is social science. Does that make sense? Yeah, this is social science. Social science uses 95%. Always. Okay. Yeah. You're expected to know that now. You know, on the exam, you should know that 95% is the standard in all social sciences and political science. Basically, in anything where life doesn't depend on it or you have to get a little lazy. And I'm going to hit calculate. And it gives us our lower and upper bound. And you'll notice I'm going to go 1 decimal because, again, no one ever cares about 2 decimal for age of first kiss on the average. So I'm going to go 1 decimal, 14.7 to 17.8. Any questions on that? Notice I programmed it so it re-gives you the X bar and S because you might care about them. So 14.7 to 17.8. Let's go back. So our confidence interval, all right, CI, is 14.7 to 17.8. Any questions on that? So one thing you might notice, which is interesting, high school. This is definitely high school time. So it looks like high school time. It could be the summer before, the summer after, but this is high school time. So high school tends to be age of first kiss. And again, my generation, it was middle school. Okay, we called it junior high school at the time, but that's what it was then. Now it's changed. Okay. Any questions? Any questions on getting this confidence interval? Any questions? Okay, so the next thing I want to do, let me copy and paste it because those are our key numbers, is I want to note a little technical thing. can I explain the confidence interval one more time? Well, we're going to continue on with it, but the confidence interval is 14.7. That's kind of our lower bound in that picture, and 17.8 is our upper bound. So that's the age bracket that we think the average, the population mean age of first kiss is likely to be. Okay, and we'll get into more detail in a bit. But I want to mention one little piece that is important. Okay, and there's an issue. And the issue comes from the central limit theorem. Hopefully you remember that sigma sub x bar is sigma over root n when we're talking about averages. Do y'all remember that? Okay, we know n, right? N was our sample size. Do we know sigma? Yeah, we don't know sigma. Okay, that's the whole population standard deviation. We don't know the population. All we got is our sample. Okay, so it turns out, believe it or not, this has everything to do with beer. You guys were thinking that, right? maybe you're just tired of stats and you're thinking about getting that beer. Okay, and I'm not kidding. There was 100 years ago or so, there was a statistician. He taught classes, but he also worked for a brewery. And what he did is he collected data to get like the best beer he could come up with. Okay, and he wanted confidence intervals. And he realized that this 95%, he'd do a 95% confidence interval, but he wasn't getting it right 95% of the time, which he should. He was getting it right a little less. And what he realized the reason is we use sigma, we used S instead of sigma, and we don't know sigma. So there's going to be an extra error. Does that make sense? There's an extra error in using S for this sigma sub x bar. And what he came up with is that he could build in that error into the normal distribution and make some adjustments and change the distribution. The math is very intense. Okay, even for Braulio, it's too intense. Just let you know, Braulio, it is brutal. So you don't have to know the math at all. But what you do need to know, is that it has a name, and he named it after his students, and he called it the student's t-distribution. So when you're doing a confidence interval for the mean, you don't use a z, you don't use the normal distribution. You actually use this adjusted distribution called the student's t-distribution. Any questions on that? Okay, so we'll end up with a t instead of a z, it turns out, because t for student's t-distribution, whereas z is your normal. So that's just a big note, is that we're going to use a different distribution. Again, the calculator does that all for you, but we're going to be doing it for the next few weeks. So I wanted to mention it now so that you've got it, that there's this issue with the standard deviation. And we're going to use the student's t-distribution to deal with the issue. And again, it had to do with this guy that worked in a brewery. So beer does stuff. All right, so now what I want to do next is understand this confidence interval deeply. So an example is our example. The question might be is find a 95% confidence interval for age of first kiss among adults involved in stats classes. We did that, and then write the interpretation. Using a full sentence. A complete sentence. And I want to let you know we're moving into the part of the class where there's going to be a lot of writing. Okay, so make sure that you get used to the writing. So what is it? So let's see if we can interpret this confidence interval. Any questions on the question? And what we say, let me write it out, is with 95% confidence, because that's what we used. Our CL was 95. The population mean age of first kiss is between 14.7 years old and 17.8 years old. And if you want first kiss for those involved in stats classes. Okay, and maybe instead of those, because I want to emphasize adults. Okay, so your 2-year-old child might be involved in it, but it's worthless to ask them when was their first kiss, because they haven't had it yet. They better not have. All right, so I want to mention a few things. Right here, population mean. Population mean is absolutely necessary in the interpretation. If you don't put the words population mean when I ask you to, okay, when I ask you to interpret the confidence interval, what do you think will happen to you? Yeah, you'll lose points. That's a guarantee. Okay, there's no, and if you really didn't get the confidence interval right, but in your interpretation you had the word population mean, I'll give you points. Okay, you got to look at the bright side too. Just remember, put the word population mean in there. That's what it's talking about. Here's another thing that's important. And width. And not that every interpretation has to start with the word width, but what I recommend is that if you start getting kind of a way of doing things and you do it over and over again, it's much easier to remember than if you write it differently every time. So I recommend starting the word with, because it gets you started and it helps to get started in terms of success. But population mean has to be there. That's an absolute. Okay, if we're talking about means, and this is definitely a mean, right? It's a quantitative question. How old were you when you had your first quiz? You're not going to say yes. You're going to give me a number. Any questions at all on the interpretation of the confidence interval? Okay, so now what does it mean to be 95% confident? Okay, so again, our picture is over here. We got this normal distribution, and we're talking about the sampling distribution. And remember, the sampling distribution is the distribution of all sample means, or basically the distribution of all the different studies that you can do, asking, and how many we have again? 3, 6, 9, 13. That's right. We had 13 different people answer this. So we had 13 different people. Well, if we went to a different 13 people, would we get the same confidence interval? If we went to a different group of 13 people involved in stats class, then you get a different confidence interval. Okay, and you could go to another 13 and get another confidence interval, right? I like to look at these confidence intervals as being winners or losers. So we have our confidence interval from 14.7 to 17.8. Okay, it's a winner if that confidence interval actually did contain the true population mean. That means what you said was actually what you wanted. Whereas if it didn't, if the population mean age of first kiss turned out to be, say, 14.2, that means you misled everyone. Does that make sense? So I like to think, and I want to let you know, one of my first jobs, not my first job, one of my first jobs was actually surveying for a market research company. Okay. I'm not the one that actually created the confidence interval, but I did this. I did this over and over and over again. And it would be good if most of my confidence intervals contain the population mean. Do you agree? But if most of mine didn't, then I'm screwing up. Do you agree? That's how surveying is, right? Here's a guess, by the way, nothing to do with this class, but just for fun. How old do you think I was when I had this job? Okay. Okay, you're gonna be in shock. Okay, here's a note. It was before my first kiss. I was 11. Life was different. Okay, nowadays that company, the boss would go to jail for having an 11-year-old employee, but things were different in those days. And one of my first jobs, believe it or not, was statistics, not because I was a statistician or anything. I was an 11-year-old kid. But that's what I did, I did surveys. Okay, I called people on the phone and did a survey and then wrote down their answers. And then someone else who knew statistics, I didn't when I was 11, created confidence intervals. And this company, if they use a 95% confidence level of confidence, then 95% of their confidence intervals will be winners, will contain the true population mean, and 5% won't. Okay, for a company that does confidence intervals. So now let me write down the answer, which is basically that. So what it says is that if many samples of 13 stats involve people, were taken, then each sample would result in a different confidence interval. Okay. So again, we asked 13 people today and we got 14.7 to 17.8. Well, if I asked a different 13 people tomorrow, I might get 14.2 to 16.5. Who knows? And then if the next day I asked a different 13 people, I'll get a different confidence interval. Every time you ask 13 people, you'll get another confidence interval. 95% of these confidence intervals will contain the true population mean age of first kiss for stats related people. Five 5% won't. 5% will not contain it. Any questions about interpreting the confidence level? Again, the confidence interval starts with the word with. Okay, so what does the confidence interval mean? That's the with. What does it mean to be 95% confident? That's this guy. That starts with the word if. Let me highlight if. And let me also highlight, because what it's all about, population mean, because those will always happen. Any questions at all on this interpretation and what it means? So is there a minimum number of times to conduct the survey to make sure 95% have it? So that's the law of large numbers. It's the same thing we did with the expected value, many. Do you remember that? And if you really want to learn about how many you have to be, say, 4 decimal places of accuracy for 95%, you need to take an advanced upper division or graduate level statistics class. But in this class, we don't talk about it. So just many is good enough. Sound good? Yeah. But if you want to learn it, become a math major like me. I learned all about it. It's brutal, but it's interesting if you love math. Okay. Otherwise, don't bother. Okay. What I do want you to know is not forgetting the words population mean. Got it? And knowing the difference between interpreting the confidence interval and interpreting the confidence level. I also want to mention another big thing about my testing. I will always ask you to interpret the confidence interval. Sometimes in slightly different words, but you're always going to be asked to do this in every confidence interval question. But on the other hand, this guy, what does it mean to be 95% confident or interpret the confidence level? I don't really ask you that more than once in a test, even if there's a lot of test problems that have confidence intervals. So just let you know that this first bit, which is easier, shorter, is more important. Okay, the second bit I do ask once, but just a note, be ready for this guy with the word with, because that's going to happen a lot, whereas this one only happens once. And I will ask you once. Any questions on this? Okay, I want to give you a template because I think some of you like to have a template instead of just an example. So here's a template. And let me start out with what I call the conclusion template or interpret the confidence interval template. And it's with XXX% confidence. That XXX, what might it be? Yeah, it'll often be 95%, but it could be a different number. But the point is, it'll be a number. So I'm running XXX because that'll change. It can be concluded that the population mean, okay, and then XXX. That's not a number. That's kind of the context of the question. In our case, it was age of first kiss for stats-related people. Okay, so that's what the XXX is. It gives context into what's going on. Is between XXX and XXX, the lower bound and the upper bound. And that's kind of a template. I mean, there's lots of ways of writing it, but some people like to have a template. Any questions on the conclusion template? Okay, then there's the interpreting the confidence level template. That's interpreting that 90. What does it mean to be 95% confident? Or 95% is a probability. What's the probability of? And what it is if many samples of whatever, okay? So that could be 13, which is what we had. So 13 stats-related students are taken. Then each would produce its own confidence interval. Whatever percent, that might be 95%, for example, of these confidence intervals will contain the true population mean, XXX, that would be, in this case, the true population mean age of first kiss for stats-related students, and whatever percent. And so if we had a 95% here, this would be a 5%. Won't contain the true population mean. Any questions on interpreting the confidence level? Any questions? Any questions? Okay, I want to note something. This is very important. And that is you need a sample size of over 30 or you really can't do it. Okay, otherwise you have to assume the distribution is normal, which is pretty bad. Any questions on that note? Okay, then finally, it won't take too long.
Wait, go back up for a second.
Okay, I need to get to what I'm going to get to. Here, wait here.
Just so I can write the templates down.
Yeah, you do remember these are all on YouTube, so you can always see it again. As long as the recording works, and most of the time it works. But with technology, you never know. Okay, can I move up? Or scroll down?
Go for it.
Okay. So we know from the central limit theorem that sigma sub x bar equals sigma over root n. Okay, that was a big, big theorem. E is z times sigma over root n, it turns out. I'm not going to get into it because we don't have time, but there's some math involved. You don't need to know the math. And then that is equal to z sigma over root n. So that means E is z sigma over root n. We can multiply by root n, divide by E, and take a square of both sides, and you get E equals z sigma, n equals z sigma over E quantity squared. Okay, that is the formula to decide how big a sample size you need. Any questions on that? Okay, now let me tell you something I did that made some people upset. Okay, my guess is you won't be those people. Is I created a calculator that made it so you don't have to memorize this formula or even use it. But most statistics classes require this. So I need to show it to you so I can say that I've shown it to you, even though you're not going to use it. Okay. But some of my friends actually were really mad when I put it in my calculator because they wanted students to use this formula. So if you get mad at me, I apologize that you don't have to do advanced math. But I decided we can only do so much. So here's an example. So suppose you want to find a 95% confidence interval for the population mean average, the mean hourly wage of nurses in California. Okay. Based on the preliminary study, which means I looked at Google, the standard deviation is assumed to be $12 an hour. If you want a margin of error to be no more than 50 cents, how many nurses must you survey? Any questions on the question? Okay, and the idea is it's going to be at least 31 because you need to be able to use the normal distribution. But if you want a small margin of error, you may need more than that. Any questions on that? Okay, so there's the hard way of doing it, and that is put it into this formula, put it in your calculator, work it out, and there's going to be multiple formulas. On Thursday, we'll have more of them. But the easier way of doing it, except that I got in trouble for it, is to use our calculator. So I'm going to go back to the calculator. Which calculator do you think I need to use? Which number? The hint is we're doing things in order. Number, not 9, number 11. Number 11, we're trying to find a sample size. How many people what is the sample size? So I'm going to do sample size for the mean. Our sigma was 12. Our E was 0.5, 50 cents. And our confidence level was 0.95. And I hit calculate N. And I get 2213, 2,213. So survey 2213, 2,213 nurses. Okay. By the way, if I made you do that for your project too, you'd be mad, wouldn't you? Okay, you'd be really mad at me probably. What's Z in the equation again? Oh, the equation. I went through the equation fast because you don't need to know it. Z is the Z-score. Okay, so Z is that Z-score that corresponds to 95%, which happens to be 1.96. So you'd have to use the normal distribution calculator to find it. And you would get 1.96 if you did it. Okay, or maybe negative 1.96. But you don't need to know that because I made a calculator so you don't have to do any of that. If you're mad at me, I apologize. Don't you agree that this was easy? But if you want the hard way, you can do it the hard way, which is the equation. But don't do it the hard way. Okay, we're out of time. We will continue with this. But what we'll do is we'll look at what we haven't done yet is proportions and more examples. And we're going to do that on Thursday. So we'll do, we've done now confidence interval for population means. On Thursday, we're going to move to proportions. And it's not much harder. It's the same idea, but it's going to be the yes, no question. And we'll have other examples. Maybe I'll do some mean examples too. So I'm going to stop the share and stop the recording.